Okay, we're starting to get into some Unit 2 review here with conditional statements and logic. In example 39, we're asked to find the hypothesis and conclusion of this statement. All complementary angles have a sum of 90 degrees. Now, typically, we'll associate the hypothesis with an if in a conditional statement and a conclusion with a then in a conditional statement, which we don't have here. When that is the case, our hypothesis you can think of as typically the front half of the sentence, or it's just the subject of the sentence. This sentence is talking about complementary angles, so that part is going to be our hypothesis. So hypothesis here would be all complementary angles. The conclusion then would be the details of that subject, and the detail for our complementary angles is that they have a sum of 90 degrees. Right? We are then asked to rewrite this conditional statement in if-then form, and all we had to do is put that hypothesis with the if and that conclusion with the then. We just need to make sure it makes grammatical sense. So a good example would be if angles are complementary, then they have a sum of 90 degrees. Right? We're going to see very similar thing here, just testing our skills on that again. In example 41 says identify the hypothesis and conclusion of this statement. Again, we don't have if and then, so we're looking for the subject, and we're being asked about all angles that are 30 degrees, or we're talking about angles that are 53 degrees. And our conclusion would be that they are acute angles. So hypothesis is all angles that are 53 degrees. Conclusion, the details is they are acute angles. Again, we are going to rewrite that now in if-then form. So again, if with the hypothesis, right? Then with the conclusion, we just need to make it make sense grammatically. We wouldn't say if all angles that are 53. We would say if angles are 52 degrees, then they are acute angles, right? If angles are 53 degrees, then they are acute angles. We're getting deeper into our conditional statements here with example 43, where we're going to be writing the converse, inverse, and contrapositive of a given conditional statement, which is this underline. If two angles are supplementary, then they have a sum of 180 degrees. Well, the converse is just flipping the hypothesis and the conclusion. So if still starts our statement, but instead of having two angles are supplementary here, we're going to take that conclusion and we're going to bring it up to the front. So we're going to say if two angles have a sum of 180 degrees, then they are supplementary. That would be our converse, okay? And that is a true statement, right? We're also being asked here to evaluate if these are true or false. That's true, right? Our inverse is then negating the hypothesis and conclusion. So that would be saying the opposite of what's happening. So instead of two angles being supplementary, we would say if two angles are not supplementary. So there's no switching in the inverse, there's just negating. So if two angles are not supplementary, then, and we also negate the conclusion, then they do not have a sum of 180 degrees, would be our inverse. Our contrapositive combines both the converse and the inverse. So we're going to flip the hypothesis and conclusion, and we're going to negate it. So we're going to bring that sum of 180 up front and say the opposite of it. So that would look like this. It would be if two angles do not have a sum of 180 degrees, then they are not supplementary to each other, right? Again, converse is switching the hypothesis and conclusion. Inverse is negating the hypothesis and conclusion. Contrapositive is doing both, and for this specific statement, these are all true statements for our conditional. We're being asked to do the same thing again. You'll find that some people, though, just get into that rhythm of doing converse, inverse, contrapositive. And here I'm just kind of putting the order, or just making the order random here of which statement you have to write. It's really going to test your knowledge of each specific type of conditional. We're given if an angle is bisected, then it is cut in half. We're first asked to write a contrapositive. Remember, that's the one where we flip the hypothesis and conclusion and negate it. So that cut in half part comes up first, and we say the opposite. So we say if an angle is not cut in half, then the bisected part goes to the back and it's also negated. Then it is not bisected, right? Which is true. If something's not cut in half, it's not bisected. Bisected means to cut in half. Converse next, remember that's the one where we only switch the hypothesis and conclusion. So the cut in half comes up front if an angle is cut in half, then the bisected part goes in the back. Then it is bisected, which is true. That's what bisect means. And then lastly, we're doing the inverse, which is negating, all right? So that angle is bisected, stays up front. We just say the opposite of that. So if an angle is not bisected, then it is, we also negate the conclusion, it is not cut in half. Again, all three of these are true statements here. Again, that is how it works for theorems in geometry. We're getting into some measurement questions here where we're finding the area of a figure. First, we need to know what kind of shape we are looking at in order to determine its area. This is a parallelogram. Our arrows on opposite sides that are matching are telling me that opposite sides are parallel. That makes this a parallelogram. And in Florida, on our reference sheet, we get the formula for the area of a parallelogram given to us when we take these standardized tests. So the area equals base times height for any parallelogram. The key is to remember heights are always perpendicular. They always have to form a right angle. So the only thing we can consider, remember heights have to be perpendicular. They have to form right angles. So the only thing that we can consider a height in this figure is that dashed segment there that is 6 centimeters long. That's typically what we should do first, is identify the height of our figure. Let me write that more cleanly. We have a height of 6. Our base then is just the side that height is measuring from. It's not always the bottom of a shape. It just happens to be the bottom in this figure because that perpendicular height is going from this side to the opposite side. That means that 12 needs to be our base, and then we can calculate our area from there. Base of 12 times the height of 6 gives me an area of 72 centimeters squared for this parallelogram. In example 46, we're asked to find the perimeter and area of this figure on our graph. We can recognize that this shape is a parallelogram, right, due to the parallel sides that are opposite on our shape. For example, these two sides that are vertical are parallel to each other. You might be able to tell visually that BC and AD here have the same slope, making them parallel in our figure, and therefore we can find the area with our formula for the area of a parallelogram, which again is just base times height. Again, though, heights have to be perpendicular. They have to make right angles, and we can actually identify a height by measuring this distance from left side to right side. We can do that pretty easily because it's countable, right? I can count across there and I get 6 for that measurement. So I get a height of 6, and if that I'm taking as my height, I would make these sides my bases for this shape because it's measuring the distance from this side to the opposite side. So this distance, again, is countable, and I can count and find out that that is 8 units long for that base. And then I can plug both of those into my area formula. Base of 8 times the height of 6 gives me an area of 48 units squared for this parallelogram. This is not the only way we could have found this area. We could have also used the box method, which would require us to put this figure inside of a box. We could find the area of that box by doing base times height. So I could count this as a base, I could count this as a height, and then I could find the area of these triangles that are inside the box by doing base times height divided by 2 for each, and then taking those away from the area of the rectangle. And that would give me the same 48 units squared for the figure in the middle. Sometimes though, we'll have shapes that are sitting nice and pretty on the graph where we don't have to worry about that. We can just count the things that matter like we did on this one. The perimeter for this one is a little bit more difficult. Remember, perimeter is adding the sides together. We have 2 sides that we can count. For example, side AB here is 8, side CD is 8. We could just count those with our fingers. Remember those slanted sides though, if we need to know how long they are, like previous examples, we need to do the distance formula on them. So for side BC, because it's diagonal, I'll have to take the location of B at -2, 3, the location of C at 4, 6, label them, and plug them into our distance formula. So x2 minus x1 squared plus y2 minus y1 squared, and then calculate, excuse me, calculate the distance from there for those sides, right? If I do the algebra correctly here in the distance formula, I'm gonna get, what am I gonna get? I'm gonna get the square root of 45 for side BC. If I did the same thing for AD, do the distance formula, which I would have to do to get the length of it, I would also get the square root of 45 units long. And from there, we could calculate the perimeter of our figure. We have 4 sides, 8, square root of 45, square root of 45. And we can add all those together in any given calculator, especially if we're doing standardized testing. You should have some form of a calculator on the test that you can easily input this and determine the answer here for your perimeter. So adding all of that up gives me a perimeter of about 29.4 units on this figure. Right, so again, area on a graph, sometimes we can count the stuff that we need, sometimes we can box it in. Perimeter is just finding the length of all of our sides. If we can count it, awesome. If we can't, we need a distance formula to figure out how long that side is. And then we add all our sides together for our perimeter. 47 and 48 are a nice review of equilateral triangles. 47 says RST is an equilateral triangle, and we have to find the measure of angle RST. I am going to just draw a triangle RST. And if it's an equilateral triangle, that means all the sides are going to be congruent to each other, and all the angles are also going to be congruent to each other. RST is this angle here in the bottom left corner. It's unknown, I call it X. All the angles would then be X because they're all congruent, and I know the 3 angles in any triangle must add up to 180 degrees. Now the algebra I've just written down here is not necessary. It's true, but it's not necessary if you can just remember that the algebra here is going to give me 60. And that must be the measure of each angle in an equilateral triangle. If all 3 of them add up to 180, then each individual angle must be 60 degrees. We can use that logic then to answer our next question that's asking me to solve for x and y in this triangle. Our dashes tell me all 3 sides are congruent, making it an equilateral, which means all 3 angles are congruent. And as we just discussed, that means each angle must be 60 degrees. So to solve for x, which is an angle in an equilateral, I just need to set that equal to 60 degrees and then do the algebra to solve. If I subtract 10 from both sides, I'm going to get 2x equals 50, divide both sides by 2, and I get 25 degrees for x. Then we do the same thing for y. That's an angle in an equilateral. It has to equal 60 degrees. So 3y plus 3 has to equal 60. We can subtract 3 from both sides to get 3y equals 57. Then divide both sides by 3 to get y equals 19 degrees in that example. Remember, equilateral triangles, the angles have to be 60 degrees each. Back to another area question here. In the state of Florida, the triangle is the only shape that we are not provided the area formula for on the reference sheet. It's because we're expected to know. Any given triangle is half of a parallelogram. Again, if I were to draw a parallelogram and draw a diagonal, it splits it into 2 triangles. Therefore, that formula for a parallelogram, which is base times height, we would just cut it in half to get the area of a triangle in there. And that is our formula for the area of a triangle. It's base times height divided by 2. And again, heights have to be perpendicular. They must make right angles. So the only thing in this figure that can be a height is that extended segment out there that is 12 feet long. So we have a height of 12. And remember, our height always measures from our base. So the side that this is measuring from is the extension of this 14 feet here, right? That distance outside of our triangle does not matter. All that matters is the actual length of the base on our triangle, which would be 14 here. So in this example, the 13 is not relevant to solve for the area here. We have a base of 14, a height of 12, and we use those in our calculation here for our area. So base times height divided by 2. We do 14 times 12, we get 168 divided by 2, gives me 84 units, this is feet squared for this triangle. Example 50 is reviewing the area of a triangle again. We're just on a coordinate plane this time, and we're actually able to solve for the area here the same way that we did for this triangle. Even though our triangle's kind of leaning, where our height doesn't look like it's pretty defined, we can find it actually outside of our triangle, just like that 12 feet there. So I can take this countable side RS and use it as my base, and if I count the distance across there, I'm gonna get 5. And then this segment that I'm drawing right here from T to level with side RS can represent the height of this triangle. And hopefully you recognize what I've drawn here is very similar to what we saw in this prior example. So again, this would be our height. It's our distance from RS to the opposite vertex of the triangle. That is countable, and that is 8 units long. And I can calculate my height from there. Again, triangles, base times height divided by 2. Don't forget, you have to memorize that formula. It's not on a reference sheet. We get a base of 5 and a height of 8. Those can then get plugged in for us to calculate. Base of 5 times a height of 8 divided by 2 gives me an area of 20 units squared for this triangle. 51 is another error analysis question. We're told the perimeter of a triangle is 45. We're given some expressions with variables for the side lengths of this triangle, and we have a student named Jenny that says this is an equilateral triangle, which it's not, and we have to correct her and explain why it's not an equilateral triangle. Let's go ahead and draw this thing to start. We have triangle ABC. We know that side AB is 4x. We know that side BC is 5x minus 5. We know AC is x. We know the perimeter is 45. Well, if this is true, we can determine the value of x by knowing the sum of these side lengths has to equal 45, because that's what perimeter is. It's adding all the sides together. So we know that 45, our perimeter, must equal the sum of 4x and 5x minus 5 and x, our 3 side lengths. We could do algebra from here to solve for x. Right, if we're combining all of our x's there on the right, we have 4x plus 5x plus x, that's 10 x's. Still have the minus 5. I can get the 10x alone now by adding 5 to both sides. So that gives me 50 equals 10x. Then I can get x by itself by dividing both sides by 10. That'll give me 5 for x here. Now, x being 5 now allows us to determine the length of our sides. So if I plug 5 into side AC, well, AC is just x, so AC would be 5 units long. If I plug it into side AB, well, AB is 4 times x, so 4 times 5 gives me 20. And then I could just stop right there. I could stop there to explain why Jenny's wrong. We could also prove by plugging in here, again, just to be certain. If we plugged into this side, 5 times 5 is 25 minus 5 gives me 20 for side BC. And so what we see is that we have 2 pairs of congruent sides instead of 3, which we would need for an equilateral. Right? So our math here proves that this is an isosceles triangle with 2 congruent sides, not an equilateral like Jenny said. Next, we have some midpoint review. We have to find the midpoint of a segment with given endpoints. There's a formula for a midpoint, and we have that on our reference sheet, so you do not have to memorize it. We do not have to use it. We have to know how to use it, though. So we're going to label our points, x1, y1, x2, y2, and we're going to plug those into our midpoint formula, which has a little shell like this because it gives us the location of a point, an x-coordinate and a y-coordinate. And we find the x-coordinate by taking our x1, in this case negative 11, adding it to our x2, which is 22, and then dividing it by 2. So we're essentially just getting the average of our coordinates here. We do the same thing with the y's. y1 plus y2 divided by 2. And then we do that calculation there on our numerator. Negative 11 plus positive 22 is positive 11. 21 plus negative 60 would be negative 39. And we could leave the answer like this. This is exact, right, as fractions, right? We could also just divide by 2 to get the decimals. Either would be fine. You would just have to look for the appropriate options on any standardized testing that you do. Negative 39 divided by 2 give me negative 19.5. So we really want to look for both of these if this is like multiple choice on a computer-based test. Our next example also involves midpoints, but not coordinate midpoints. We're instead told here that on segment SU, T is a midpoint. That means it's exactly halfway between S and U, which means that ST has to be congruent to TU. So to solve for X here in this problem, we just need to set these values equal to each other. 8X plus 11 must equal 12X minus 1, and we can do the appropriate algebra, excuse me, from there to solve for X. I like moving my smallest x, so I'm going to subtract 8x from both sides. Let's cancel on the left to give me 11. Let's have 4x minus 1 on the right. I can add 1 to both sides to get 4x alone. 12 equals 4x, then I can divide both sides by 4 to get x equals 3, which again, we have to be careful. That is not the answer to the question. The question is asking me for the length of SU. Again, we need to be careful on tests and answer what's being asked of us so that we can earn credit, because if I say the answer is 3, I'm wrong. That's not how long SU is. So I'm going to plug that into ST. 8 times x, which we've solved, is 3, plus 11 would give me a value of 35 for ST. If I plugged it into TU, I'd have 12 times 3 minus 1, which would also give me 35, which we knew from the beginning they had to be congruent to each other. And then SU is just the sum of those two segments. So 35 plus 35 gives me 70 units in length for segment SU. In example 54, we have a linear pair that we're going to be using to solve for the measure of angle DBC. Let's first make sure you know where angle DBC is, and know it's not just like highlighting and saying this is angle DBC. It's knowing that the interior there is angle DBC. So 5x minus 22 is what we need to solve. So we have to find x and sub it in there to get the measure of that angle. It starts with recognizing we have a linear pair. Side by side on a straight line, these angles are supplementary to each other. So 5x minus 22 plus 8x plus 46 must equal 180 degrees. And we can do our algebra here to solve this linear pair. We have like terms, 5x and 8x giving me 13 x's. We have like terms, negative 22 and positive 46 giving me plus 24. I can then get 13x by itself by subtracting both sides by 24. That'll give me 13x equals 156. I can divide both sides by 13 to get x equals 12, which I can then plug into the measure of angle DBC, which again is the 5x minus 22. So 5 times our x of 12 minus 22. 5 times 12 is 60. 60 minus 22 gives me 38 degrees for the measure of angle DBC. All right. Our next example is going to be very similar. We're going to be using linear pairs to solve for the variables x and y. I think most students, when they see examples like this, are drawn to the vertical angles across from each other, but we'll notice our vertical angles don't have the same variables, x and y and x and y. Therefore, we cannot use those equations to solve. Instead, we're going to have to look at the linear pairs that have the same variables. These two here are a linear pair. Therefore, we can solve for x by stating that 4x plus 10 plus 13x has to equal 180 degrees, and we can do our algebra from there to solve. 13x and 4x combined to give me 17x's. Still have the plus 10. I can get that 17x alone now by subtracting 10 from both sides. It gives me 17x equals 170. I can then divide both sides by 17 to get x equals 10. And we're going to do the same thing for y using this linear pair. We just have a little bit more unique algebra involved there. So we have 2 times y plus 25 plus 2y minus 30 equaling 180 with that linear pair. And we're doing algebra to solve. We just have distribution that has to happen up here. We have to do 2 times y to get 2y, and then 2 times 25 to get positive 50. And then we can go on combining like terms and solving for y. So we have like terms, 2y plus 2y gives me 4y's. We have positive 50 minus 30, that leaves me with positive 20 after combining those. I get 4y alone by subtracting 20 from both sides, and it gives me 4y equals 160. Then I can divide both sides by 4 to get y equals 40 degrees in this example. All right, next up, we have several true or false questions that relate to the picture that we have here on board, the figure that we have. So first off, it's true or false, angle INM is a supplementary to angle KNL. Let's identify where these angles are. INM would be this angle here, KNL would be this angle here. These are not adjacent to each other on a straight line, so we do not have evidence that these angles would add up to 180 degrees. Therefore, this is false. We do not know that INM is supplementary to KNL. Next, we have angle INJ is congruent to angle MNL because they are vertical. So again, let's find them. INJ is right here. MNL is this angle. Those are absolutely vertical. They are across each other at the intersection of two lines. That for sure is true. Next, we have angle MNL plus LNK plus KNJ equals 180. Let's see. Remember, 180 we want to think of in figures like this as straight lines. Straight angles give us 180 degrees. So here's MNL, here is LNK, and here is KNJ, the three angles in that equation. And notice those are all on one side of my straight angle MNJ. Therefore, this is true. They have to add up to 180 degrees. Next up, we have INJ plus INM equals 180 because they're vertical. I don't even have to look at the figure. Okay? Vertical angles are congruent. They don't add up to 180. So even though these specific angles in here, JNI and INM, do add up to 180, they don't add up to 180 because they're vertical. They add up to 180 because they're a linear pair. Right? Vertical angles are congruent to each other, not supplementary, so that's false. Right? Last one says KNL is 90 degrees. KNL is this angle right here. And notice that on completing the straight angle INL, on the other side of KNL is KNI, which is 90 degrees. And since straight angles are 180, this angle does also have to be 90 degrees to give me that 180 there. So that is true. In example 57, we're solving for the measure of angle AOD. That is this angle right here. We already know part of it is 60. We need to find this other measure here and add it with 60 to get AOD, which means we need X first. In order to do that, we need to understand that AOB here is a straight angle. Straight angles are 180 degrees, so that means all of this on one side of my straight angle must add up to 180 degrees. So we got a pretty long algebra equation here. 60 plus 3x plus x plus 10 plus 2x plus 20 has to equal 180 on my straight angle, and we're doing algebra to solve. We got a bunch of like terms here. 3x plus x plus 2x, that is 6 x's, right? We got 60 plus 10 plus 20, that is 90. And I can get 6x alone by subtracting 90 from both sides. That gives me 6x equals 90. Can divide both sides by 6 to get x equals 15. And now I can plug that 15 in here to find the measure of angle COD. Will equal 3 times 15, which is 45 degrees. So I know now that this angle is 45. And now I can find AOD by doing that angle addition there, 60 plus 45. So the measure of angle AOD equals 60 plus 45, which gives me 105 degrees in this example. All right, in 58, we're back to a proof here for congruent triangles. We're given two triangles with two sets of congruent sides. We're being asked to prove that angle A is congruent to angle D. Well, anytime we're proving things are congruent in triangles, we first need to prove that the triangles are congruent. So we're going to be doing that in our columns here. Remember, left column is statements, right column is evidence that those statements are true. We're being lawyers here as we go through. Proofs typically start with our given information. Notice in the second statement, that right there is not one of the things that's given to us. So we are cramming all of this here into our first statement of our proof. So we're going to start off by saying AC is congruent to DC and BC is congruent to EC. That stuff is true because it was given to us. Next, we're told that BCA and ECD are congruent. Notice there's no mention of those angles prior in the proof. That means the evidence for this must come from our figure. So angle BCA is this angle right here. This says it's congruent to angle ECD, which is this angle here, and hopefully you can recognize those are vertical angles. So the reason those angles are congruent is because all vertical angles are congruent. Vertical angles are congruent. Be the reason that goes there. That marking now gives us enough criteria to say that these triangles are congruent. Notice statement 3 says triangle ABC is congruent to triangle DEC. That is because of our side angle side congruency theorem. We have enough evidence for that. Two sides in each triangle with the included angle being congruent, side angle side theorem. We need to remember from there, we've already proven the triangles are congruent to each other. So now any corresponding parts must also be congruent to each other, like angle A and angle D. Notice angle A is the angle at the end of the side with one dash, so is angle D. Those are corresponding angles, and because we've already proven the triangles are congruent to each other, we can now say that those angles are congruent because corresponding parts of congruent triangles are congruent. CPCTC to finish out this proof. Try to recall this, it'll help you out. Anytime you prove triangles are congruent, anything that comes after it in a proof is going to be true because of CPCTC. All right, in example 59, we're writing a bunch of function notation rules for transformations that happen on our graph. It'd be a little bit nicer if we had prime points on this first one. We're going to assume that this is a reflection that has occurred over the x-axis. So you can see all these points flip the same distance over this line. A is 2 OA, D is 2 OA, C is 4 OA, so is F, B is 6 OA, so is E. So this is a reflection over the x-axis. Function notation, though, is describing the change of coordinates that occurs. So if we're looking at A and D as similar coordinates, we start at -6, +2, and we transform into -6, -2. So what changed? Well, the x didn't, it stayed exactly the same. So we're gonna say the same thing here, x stays x. But the y coordinate changed its sign, it went from positive to negative. So my y needs to show a change of signs. That's our function notation for this transformation. xy becomes x, -y. We're looking at a translation in this one where all of our points have slid the same distance and direction. We can describe that with the function notation. xy becomes x. We're sliding to the right. It's going in the positive direction on the x-axis. So that means we're going to be doing x plus. And we're just counting how far to the right we have to slide. To get to A prime, from A, I'm going 1, 2, 3, 4 to the right. So that would be x plus 4. Then we're going up from that location to get to A prime, and we're just going up 1. That's going in the positive direction on the y-axis. So that would be y plus 1. So if we look at any individual coordinates here, if I add 4 to the x and add 1 to the y, I would end up at these prime locations in that translation. Right, next we have a dilation. How do we know it's a dilation? Because our figure got smaller or bigger. That's your key that a dilation happened. When we do dilations, we're multiplying our pre-image by a scale factor. Okay, so we just need to figure out what that scale factor is in our problem. And we can do that by just counting some sides. Like AB, we have 2 units long on our pre-image. On our image, it's only 1 unit long. Remember, your scale factor is a measurement from your image over the measurement from your pre-image, corresponding measurement. So it's 2 over 1, which is 2, which means that, oh, I'm sorry, I actually got the order of this wrong. My apologies. It's image over pre-image, and this is the image, right? So my image 1 over my pre-image 2 gives me a scale factor of 1/2 here for this dilation, which means that the coordinates on my pre-image would be multiplied by that scale factor of 1/2. So this is your function notation. You take those locations on your pre-image, you multiply them by 1/2 to get the locations here on your image. Lastly, we have a rotation, right? So again, all function notation starts the same way. We say xy transforms into, we describe the change. Memorizing the rules for rotations can be a little bit challenging, so I'm just going to show you here using some coordinates. Let's pick out point A here. Notice it's halfway between 0 and 2, so we're going to assume the x coordinate there is +1. And let's look at my pre-image. I did the same mistake again. Look at my pre-image. So we have -2 here for point A on our pre-image. And then we're going up halfway between 0 and 2, so we're going to assume that's a 1 there. So -2, +1 is where we start. That transforms into A prime, which is going half the way from 0 to 2. So we're going to say +1 for that x coordinate, and then it's going up to 2 on the y-axis, +2. So what changed here? Well, the 2 went to the back, and it went from negative to positive. The y went to the front, but it kept the same exact sign here, so we just need to say that in function notation form. So again, this switched and went to the back, so that means these have to switch. Y's got to come up front, x has got to go in the back. And that original x-coordinate changed its sign. So that means this needs to have a different sign than this one. So that's the function notation. xy becomes y, negative x. Next, we have two rotations here that we're going to be describing without using function notation. So not like that last one that we did here where we're evaluating coordinates. So this now requires us to have a good understanding of direction, like clockwise and counterclockwise, and the rules for movement of the quadrants when we're rotating a certain amount of degrees. So we'll start by saying the red figure is our pre-image because it does not have the apostrophes on it. It's our original shape. And it's going here from quadrant 2 to quadrant 1. It's moving in a clockwise direction. Right? So that's part of my description here. And then I just need to know how many degrees. And the rule is, however many quadrants we move 90 degrees. Sorry, let me clarify that. Every single quadrant we move is 90 degrees of movement. So going from 2 to 1 means that we've gone clockwise 90 degrees. All right, we actually get the same exact type of rotation here in this one. We have a pre-image up here in quadrant 1. We could say it's going clockwise to get down here to quadrant 4. Right, again, moving like a clock to get from here. And again, it's only moved one quadrant down, so that's 90 degrees. We could also describe the same thing counterclockwise, though. We could very easily say, well, we're going this way to get there. And that would move 1, 2, 3 quadrants, so it would be 93 times, which would be 270 degrees counterclockwise. In example 61, we have the composition of transformations to perform here. We have triangle ABC, our pre-image. We're first asked to translate with a vector of positive 7, negative 4. Remember, translations are slides, and the values here work like coordinates, like we're plotting a point. The first one is your x coordinate, and a positive 7 would mean going to the right 7. The second one's your y coordinate, a negative 4 would mean going down 4 on the y-axis. So we're going to start off by sliding 7 to the right, 4 down for each point on our pre-image. My red here is just my counting. There's 7 to the right and then 4 down, and that is where A prime will be located. And we're going to do that again with each point. So with B, there's 7 to the right, 4 down. That is B prime. Keep this up in red, B prime. And then we have C prime. So we're going 7 to the right, 4 down. There is C prime. So that is our first image for a triangle ABC. Got ABC prime. Then we're asked to reflect this over the x-axis. So our x-axis is our blue line here. I'm going to make that stick out a little bit more with this. And we have to flip our points over that line. Remember, reflections are flips. We just need to figure out how far away our points are from the line and flip them. And again, we're taking our most recent image, not our pre-image. We're taking this shape to reflect it over the x-axis. Starting with A prime, we can just count it's only 1 unit away. So a double prime will be 1 unit away on the other side, right there, a double prime. Right, B prime is 1, 2, 3, 6 units away. We need to go the same distance to the other side, which would put it right here, B double prime. And then C prime is only 2 units away. So 2 units away on the other side, C double prime. And that is our composition of transformations done here in this example. In our next 2 examples, we are being asked to describe transformations that have occurred on a graph. And here we have 2 that have happened. So we need to describe both of them in the order that they happened, right? And just to help you out in case you're having a hard time seeing, this will be your pre-image. This is our first image. This is our second image, right? So we first need to figure out what happened here. And again, there's indicators here that a reflection has happened. It looks symmetrical over the x-axis. We can also look at the midpoints of A to A prime, C to C prime, B to B prime, and determine that those are all on the x-axis. So that means that this is a reflection over the x-axis. Next, we have to describe the transformation that gets us from this triangle to this one. And this just looks like a slide, like all of our points have just gone to the left. And that is a translation. Translation. And again, I like describing translations with function notations. You could also do a vector. You want to avoid just using the words left, right, up, or down. Okay, but counting from A prime to A double prime, we can see that's 1, 2, 3, 4, 5 to the left. Same 5 for B, same 5 for C gives me a translation. Here's the function notation for that. If we're going to the left, that means we're subtracting from our x coordinates. And we subtract the same distance we travel, so that's x minus 5. Notice our points did not go up or down at all, so that means the y coordinate just stays the same. This is a description of the transformations in here. Started with a reflection over the x-axis, then a translation 5 to the left, right? We had to describe transformations again. Our pre-image is our solid figure here. Our first image is this shape. Our second image is that one over there. So again, we have 2 to describe. And again, we're starting with a flip here just over the x-axis. C and C prime stay at the same location. That's an indicator, good indicator that you've reflected over a line that contains that point. And notice that the midpoint of A and A prime would be there at the same place. The midpoint of B and B prime would be here. If I connect those, that gives me the x-axis. This is a reflection over the x-axis to start. And then we're following that up with another translation because we can see that our points A to A prime have gone right and up, B to B prime, right and up, C prime to C double prime, right and up. All our movements here from primes to double primes are going the same distance to the right, the same distance up. And we can count those. We have 6 units to the right, 2 units up for all 3 sets of points from B prime to B double prime. 6 right, 2 up, C prime to C double prime. 6 right, 2 up. So we can write that in function notation form. XY becomes 6 to the right is adding 6 to the x, 2 up is adding 2 to the y. That is our description of the transformations in this example. Before we're told CM is a segment bisector, we have to solve for y. Remember, to bisect something means to cut it in half. So that means M here would have to be the midpoint of AJ, splitting this in half, meaning this half AM would have to be congruent to this half MJ. So these 2 expressions here can be set equal to each other. 5y plus 8 must equal 8.2y, and we can do algebra from here to solve. You may not be used to having decimals as coefficients, but it's fine, it can happen, and we can solve for it regardless. I get my y's to the same side, I'm gonna subtract my smallest y's here from both sides. It leaves me with 8 on the left equal to 3.2y on the right. Then I'm gonna divide both sides here by 3.2 to get y equals something, 2 point something. Let's see, 8 divided by 3.2 gives me, 8 divided by 3.2 gives me 2.5 for y in this problem. The next question is kind of a follow-up here. It asks us, why would it not be possible to solve for y if CM was not an angle bisector? Well, the answer to that is that we would not know that AM was congruent to MJ, right? This wouldn't be true. AM would not be congruent to MJ if we did not have a segment bisector. Therefore, we would have no idea about the lengths. We would have no idea what equation would allow us to solve for y in that problem. In our next example here, we are describing a dilation, right? It says describe the transformation. We should be able to recognize this as a dilation because our figure has gotten bigger or smaller. And the only transformation we've learned of that does that is a dilation. Now the key here is going to be knowing what is the scale factor of the dilation. Well, we first identify our pre-image as our smaller triangle. So we've gotten bigger, so that means we have an enlargement. Our scale factor would have to be greater than 1. And we can find out exactly how large that scale factor is by looking at corresponding measurements between our image and our pre-image. For example, on our image, I can see that side AB prime is 6 units long. And on our pre-image, I can see that side AB is 2 units long. And I can determine my scale factor from then, knowing that my scale factor is just my image over my pre-image. So for my image, side AB prime was 6. My pre-image, that side was 2. Therefore, my scale factor here is 3. This is a dilation with a scale factor of 3. In example 67 and 68, we have partitioning questions here, right? Very important to review these because this is a very unique thing in geometry. The math that's involved with this is not super similar to any other math for us to recall on. So make sure you have this process down. We're finding a part that's going to split a segment into two different pieces, and we're given a ratio about the measurement of those pieces, 2 to 3 in this case. Well, in order to figure out where this point is located that gives us this ratio, we're first going to need to know the distance between our points, and the easiest way for us to find that is to use our slope formula in this problem. So I'm going to label my points, and I must label the first point in the name of my segment with the 1s in order for this to work, right? Because we have direction involved here. From A to B, we're given a ratio of 2 to 3. So A's got to be my 1s, and we're going to find the slope between these points. The slope formula is y2 minus y1 over x2 minus x1. So we're going to plug in here. My y2 is 3 minus my y1, which is negative 2, over my x2, which is negative 11, minus my x1, which is 4. 3 minus negative 2 is 5. Negative 11 minus 4 is negative 15. What we're doing now is saying, like, okay, the distance between my y's is 5 units apart. The distance between my x's is negative 15 units apart. My point, though, is going to be a fraction of these distances. And we can find that fraction from this ratio given to us, right? So we can imagine it like this. In a segment, if I have 2 parts before a point and 3 parts after, that is a total of 5 parts, and there's 2 parts before the point. So we can say that this point is 2/5 of the distance from end to end. Right, and that again we can find from this ratio. So we're essentially saying, okay, 2 plus 3 gives me 5 total parts. My first point has 2 parts before it. So I'm using a fraction of 2/5, 2 out of 5. That means I need 2/5 of these distances. So I'm multiplying both by 2/5. 5 times 2 divided by 5 will give me 2 for that value up top. Negative 15 times 2 divided by 5 will give me negative 6 for that value on the bottom. Then again, this came from y coordinates, this came from x coordinates. These now represent how far away my point is from the start of the segment, which was point A. So I started this segment at positive 4, negative 2, and I know that I need to be negative 6 units away from this x coordinate, so I'm going to subtract 6 from it. 4 minus 6 gives me negative 2. I know I need to be positive 2 units away from my y coordinate, so I'm adding positive 2 to the y coordinate. Negative 2 plus 2 gives me 0. Therefore, my partitioning point is located at negative 2, 0. Our next example is very much like this. Be able to go through it a little bit quicker here. We're finding a point that partitions CD with a ratio of 2 to 1. We're going from C to D. So C is my 1's, x1, y1. D is my 2's, x2, y2. Again, we're starting with slope. We have y2 negative 12 minus y1, which is 9, over x2 8 minus negative 1 for my x1. Negative 12 minus 9 gives me negative 21. 8 minus negative 1 gives me positive 9. Right? We have a ratio of 2 to 1, meaning wherever our point is, 2 parts before it, 1 part after. That's a total of 3 points, with 2 coming before our point. That's 2/3 of the distance from start to finish. So we need 2/3 of these distances between our coordinates. So we're multiplying both of these by 2/3. Negative 21 times 2 divided by 3 is negative 14. 9 times 2 divided by 3 is positive 6. Again, this came from my y's, this came from my x's. These represent how far away our point is from our starting location, which was C at negative 1, positive 9. Again, 6 away from my x's, so I'm adding that to the x here. Negative 1 plus 6 gives me positive 5. Negative 14 away from my y's, so I'm subtracting 14 from my y here. 9 minus 14 gives me negative 5. My partitioning point is at positive 5, negative 5. Next up, we have some review of parallel lines and the angle pairs that are created by them. So we have 2 lines parallel here. We know they're parallel because they have matching amounts of arrows on them. The angles that are given are in between the parallel lines, but they're on opposite sides of this transversal. That makes them alternate interior angles. And alternate interior angles are always congruent on parallel lines. So 8x minus 4 would equal 60. We can then do our algebra here to solve. Adding 4 to both sides will give me 8x equals 64. I can then divide both sides by 8 to get x equals 8. Our next example, again, it gives us lines that are parallel. It says so right here, line 1 is parallel to line 2. We have to solve for x. These angles here are in between the parallel lines, but they're on the same side of our transversal. That makes them consecutive interior angles. And consecutive interior angles are supplementary on parallel lines. They have to add up to 180 degrees. All right, so 3x plus 20 plus 2x equals 180. We can combine these like terms. 3x plus 2x gives me 5x's. Still have that plus 20 there. I can get the 5x alone by subtracting 20 from both sides to give me 5x equals 160. And I can then divide both sides by 5 to get x equals 32 degrees for this example. So the last two examples, alternate interior angles are congruent, consecutive interior angles are supplementary. We're going to be combining both of those to solve 71. We have multiple lines given, but we're told R and S are parallel. So line R parallel to line S. T and U are parallel. So line T parallel to line U. We can look at one angle pair at a time. For example, if I ignore all of this on this side, I can look at this angle pair between the 5A and the 85 that are on these three lines, T, U, and R. They're in between T and U, which are parallel, on the same side of a transversal. That makes them consecutive interior angles. And therefore, we can solve for A by knowing that 5A plus 85 equals 180. I can subtract that 85 from both sides, and I get 5A equals 95 degrees. I can divide both sides by 5. A would be 19 degrees in this example. I can then solve for B by ignoring the stuff up here and looking at these two lines in U. So R is parallel to S, U is the transversal. Those are alternate interior angles between the parallel lines, but on different sides of my transversal. And alternate interior angles are congruent to each other. So those need to be equal in value. That 15B plus 10 must equal 85. Again, we can do the algebra to solve. I can subtract both sides by 10 to get 15B equals 75. And then I can divide both sides by 15 to get B equals 5 degrees in this problem. Got more involved with parallel lines here on example 72. Again, the same kind of scenario where we have multiple parallel lines like we did here, but we have different angle pairs that are involved with this one. So if I ignore what's going on down here, with line A being parallel to line B, we have this transversal C giving me angles outside of my parallel lines. These are alternate exterior angles which need to be congruent to each other. So 3x plus 20 has to equal 140. And we can do the algebra to solve. I can subtract both sides by 20. That gives me 3x equals 120. Can divide both sides by 3. X equals 40 degrees. Now to solve for y, I can ignore what's going on down here, knowing that these lines are parallel, C and D, as it says here. The challenge in this one, though, is that I do not have a direct angle pair there between the 140 and the 2y minus 6. However, if I know this is 140 and these lines are parallel, that means I'm going to have other 140s. For example, this angle and this angle are vertical to each other, so this would also be 140 degrees. This angle and this angle are corresponding angles. These are alternate interior angles. Either way, those are congruent. This is 140, right? These are alternate exterior angles here. These are corresponding angles. These are vertical. Either of those pairs give us congruent angles. This has to be 140. And solving for y, we can now see a better angle pair there. It's a linear pair with my 140s. So solving for y would be saying that 2y minus 6 plus 140 equals 180 on that straight line. And we do the algebra from here to solve, right? We have like terms there on the left. Negative 6 plus 140 gives me positive 134. I can subtract that positive 134 from both sides to get 2y equals 46, and I can divide both sides by 2 to get y equals 23 degrees in this example. Quick follow-up to the previous example, whereas why would it be impossible to solve for x if A was not parallel to B? Okay, so assuming that these two lines were not parallel, why could we not solve for x? Well, these would be alternate exterior angles, but we only know they're equal to each other if the lines are parallel, right? So we have all these angle pairs that exist no matter if lines are parallel or not. There's consecutive interior, alternate interior, and so on. We only have specific math that applies though when the lines are parallel to each other, right? So if we did not have that information, it would not be possible to know the value of x. We had to know that these lines are parallel to this at the start in order to set up our equation to get x equals 40. In our last example, we have several true or false statements to evaluate pertaining to this figure. First off, if r is parallel to s, then angle 1 is congruent to angle 15. Let's first just determine what lines are relevant for angle 1 and 15. We can see angle 1 is here, angle 15 is here. These angles are created by the intersections of line T and line R for angle 1, and then line U and line R for angle 1. So the relevant thing here to know that 1 is congruent to 15 would be line T being parallel to line U, and that is not what this statement says. This says if R is parallel to S, then these are congruent. And that would not be true in this example. So that is false. We need the relevant lines to be parallel in order for these alternate exterior angles to be true. We're going to continue using this logic throughout the rest of our examples. If R is parallel to S, then angle 1 is congruent to angle 5. So again, let's find the angles. There's 1, there's 5. Our relevant lines would then be this line in R for angle 1, this line in S for angle 5. And we can see where I have these angles, they're in corresponding positions, top left and top left. So we do have the relevant lines here, R and S, being parallel, mean these corresponding angles are congruent. So that statement is indeed true. In our next one, we have 3 congruent to 5 if R is parallel to S. All right, here's 3, here's 5. Again, 3 is made at the intersection of T and R. 5 is at the intersection of T and S. Again, we have the correct lines here. The relevant lines for 3 and 5 are R and S. If those are parallel, that makes these alternate interior angles, which have to be true, congruent to each other in that example. All right, next up, we have angles 13 and 3 being congruent. So here's angle 13, here's angle 3. Those are created by the intersections of T and R and U and R, not by R and S. So therefore, we have the wrong lines that are not relevant for that angle pair. So these would not be congruent, right? We have the wrong parallel lines. Next, we have angles 16 and 10. Here is 16. Here is 10. Those are created by the intersections of U and R, and then U and S. So we do have the correct lines being parallel here, and these are alternate exterior angles, which are always congruent on parallel lines. That is true for that statement. Here's our last one involving lines R and S. We have angle 4 congruent to angle 8. Here's angle 4, here's angle 8. 4 is created at the intersection of T and R. 8 is at the intersection of T and S. So we do have the relevant R parallel to S here. We have corresponding angles again, both in the bottom left. That is true. Right now we have a switch up with the rest of our statements. We are now saying that T is parallel to U for the rest of them. So we're using our same logic. Again, we need the relevant sides or the relevant lines involved here. So our next one to evaluate. If T is parallel to U, then angle 11 is congruent to angle 5. Well, here's angle 11. Here is angle 5. Those are created at the intersection of T and S and U and S. So we do have the correct lines involved here. If these are parallel, we get this angle pair of alternate exterior angles, which are indeed congruent to each other on parallel lines. So this one is true. Circled the wrong one there, my bad. On to our next one. We're evaluating. If T is parallel to U, then 15 is congruent to 11. Here is 15. Here is 11. Those are created at the intersection of U and R and S and U. And again, those are not the relevant lines here. If T is, these are the relevant lines, but T and U are not. If T is parallel to U, that has no effect on the congruency of these two angles. So we cannot prove that that is true. That would be false. In our next statement, we have angle 9 congruent to angle 7. Here is angle 9, here is angle 7. Those are created by T and S for angle 7, U and S for angle 9. And we do have the relevant lines here on this one. Those are alternate interior angles with T being parallel to U. They have to be congruent. That would be a true statement. Our next one is angle 1 congruent to angle 15. Angle 1's here, angle 15's here. Angle 1 is created at the intersection of T and R. Angle 15's at the intersection of U and R. And again, if those lines are parallel, T and U, that does give us that math fact here. These are alternate exterior angles which have to be congruent on parallel lines. Down to our last two. 7 congruent to 10. Here's 7, here's 10. I don't even have to look at the lines involved here. Those are consecutive interior angles which are never congruent on our parallel lines, right? We have a false statement here, regardless of which sides are parallel or which lines are parallel or not. Consecutive interior angles are supplementary. They have to add up to 180, not necessarily congruent to each other. And our last statement, angle 16 congruent to 6. Here's 16, here's 6. Those are created by the intersections of all lines. That angle is created by the intersection of U and R. The one up top is created by the intersection of T and S. These are on unconnected intersections. Therefore, we do not have any proof that these are going to be congruent to each other, right? Guys, this wraps up our review for the semester 1 of geometry, right? If you have standardized testing coming up, all these problems, understanding how to do them are gonna help you out greatly. Remember guys, you can do difficult things. Study hard in this semester strong. We'll see you in semester 2. Bye guys.